Good morning, everybody. Sorry for the delay, technology issues, but we're back with our conversations with colleagues. And I can't advance. There we go. Okay. As you know, this is roughly monthly presentations, depending on travel schedules and so on the fourth Thursday of the month. And what we've been doing is pulling together experts in the fields of earth, materials, and social sciences. And we have expanded on some occasions outside of that realm of disciplines. And this gives the opportunity for the residents to ask speakers questions. We used to be able to get together for lunch, but COVID has kind of inhibited that lately. But Jim will let you know how he would like to accept questions through his presentation. Before we start with our today's speaker, I want to tell you who's coming up. Annie Taylor will be here to tell us a bit more about distance education, particularly in the post-pandemic environment. Erica Smithwick will talk about the role of wildfire on ecosystems functions in March. Bill Brune is scheduled for June, I think. Colleen will correct me at some point if that's not correct, to talk about lightning-induced chemistry in atmospheric science. Really interesting stuff. And I'm trying to nail down Bill Easterling from the National Science Foundation to talk about their initiatives on the environment. I'm hoping for maybe April or May in that regard. But today's speaker is Jim Kasting. Let's see, I see some people entered the waiting room. I admit all, okay. There. Okay, and Jim got his degrees at Harvard and at Michigan. He's an Evan Pugh Professor of Geosciences and Meteorology. He's been at Penn State for roughly 20 years, and he's a fellow of the National Academy of Sciences, the International Society for the Study of the Origin of Life, the American Geophysical Unit, and the American Academy of Arts and Sciences. He's also the Oparin Medalist in the International Society for Studies of the Origins of Life, and he served on oodles of committees, both internally and extramurally, for the American Academy for the Advancement of Science, the NRC, National Academy of Science, and so on. His research focuses on the evolution of planetary atmospheres and climate, and on the question of whether life might exist on planets around or on other stars. So, without any further ado, let me welcome Jim. And Jim, let people know how you'd like to entertain questions, whether or not you'd like to do it during your talk or at the end. It's up to you. Thank you.
Okay, thank you, John. On the questions, I'd be happy to take them during the talk. I think the way to do that would be to raise your hand under reactions. That's where it's moved now on Zoom. There's a raise hand feature. And John, if you're able to monitor that, then you can just verbally interrupt me and tell me I've got a question. Okay?
I will do that, yes.
Colleen has her hand raised right now.
And I can't see everybody. Let's see.
Wait, for some reason, I'm disabled on screen sharing here, even though I'm the host. Can somebody re-enable me?
Colleen, can you do that?
Can do.
I see Forrest is on twice. Do you have twin?
Okay, can everybody see that?
Yes.
All right, so as John said, I work on planetary atmosphere evolution and climate evolution, and I've worked on and off with NASA for many years, and what I'm most interested in with NASA is their search for life on planet around other stars, and I'll talk about that mostly during this talk. There's 4 parts to the talk, but it's not that long because each part is fairly short. I'm going to start out with the basic requirements for life, then define the habitable zone, which is something I've worked on myself over the years, talk about a few recent developments in the search for habitable exoplanets, and finally talk about what to me is most interesting: how can we observe potentially habitable planets in the future? For the requirements for life, I'll be very brief here. I think the most basic requirement is you need a planet with a liquid or a solid surface. That means no gas giants like Jupiter or Saturn. And the reason is pretty simple, because you need, for life to get started, you need a stable pressure temperature environment on which single-celled life could evolve. I rarely get disagreements when I pose that as a requirement. Second, you need a thermodynamic free energy gradient to drive metabolism and growth. For planets like the Earth that have biospheres at their surface, then energy from the sun, in our case, or from the star can provide that free energy. So that's pretty easy for surface life. Third, availability of carbon and other bioessential elements, which we like to call schnapps. Life on Earth is carbon-based for very good chemical reasons. Carbon forms very complicated compounds, and if there is life elsewhere, it's most likely based on carbon. And again, there's pretty widespread agreement on that. So then the fourth requirement, which is really more what this talk is all about, is that life on Earth requires liquid water during at least part of its life cycle. There are organisms that can form spores, for instance, and get by without water for a long time, but in order to reproduce and metabolize, they have to have liquid water. And so I'm going to assume that life elsewhere has that same requirement, although there certainly are astrobiologists that postulate that you could have life on, say, on Saturn's moon Titan, which has liquid methane. But we're not going to speculate. I'm not going to speculate on that in this talk. The other bullet point on this slide is that subsurface water is not interesting from the standpoint of this particular talk. Subsurface life might exist on planets or moons within the solar system, like Mars, or Saturn's moon Enceladus, or Jupiter's moon Europa. And there we can potentially go there and look for it. But this talk is focused on looking for life on planets around other stars. If the life is subsurface there, then it's not likely to be visible from remote distances. We need life that's at the surface, hosted by liquid water, and capable of modifying the planet's atmosphere in a way that we can observe it remotely. So that leads to part 2 of the talk, the definition and boundaries of the habitable zone. The habitable zone, I learned just in the last year or two that it was actually, that term was defined by Walter Maunder in a 1913 book entitled Are the Planets Inhabited? But I learned about it from some papers by Michael Hart in Icarus in 1978. He defined the habitable zone as the region around a star in which an Earth-like planet can maintain liquid water on its surface at some instant in time. And then he also defined a term called the continuously habitable zone, which is the region in which a planet can remain habitable for some specified period of time, which we usually take to be 4.6 billion years for our own sun, because that's the age of the solar system. And the reason you have to define these terms is that all stars brighten as they age. As they convert hydrogen to helium in their interiors, they get brighter. Our own sun was about 30% less bright 4.6 billion years ago, and it's brightened more or less linearly since that time. So if the habitable zone at some time T0 went from here to here, if you can see my pointer, at some later time T1, when the sun had brightened, the habitable zone would go from here to here, then this overlap between the two regions is what Hart called the continuously habitable zone. All right, I was a graduate student at Michigan when these papers came out, and I was actually quite dismayed by Hart's papers. So he ran a a relatively simple model of made up a planet and ran a computer model to see whether it could maintain liquid water. He concluded that if the planet, the Earth-like planet, formed closer than 0.95 AU to the sun, 1 AU is 1 astronomical unit, that's the mean Earth-Sun distance. In Hart's model, if the planet formed closer than 0.95 AU, it would experience a runaway greenhouse at some point in its history. And if it formed beyond 1.01 AU, it would experience runaway glaciation. And in Hart's model, if a planet became totally glaciated, then it could never escape from that. And I'll show you in a moment that that was probably a mistake on his part. He wrote a second paper in 1979 where he applied the same model to planets around other types of stars and concluded that their continuously habitable zones were even narrower or in some cases non-existent. And so the corollary to this was that Earth might be the only habitable planet in our galaxy. In fact, you can still see that if you look at some old astronomy textbooks, the pessimists picked right up on that. And you can see that in the last chapters of some older textbooks. Now, as I already mentioned, Hart concluded that a fully glaciated planet could never deglaciate by building up CO2. We have empirical evidence that that's wrong because, I'm in a geoscience department at Penn State. So we think that the Earth actually did freeze over either completely or almost completely at least 2 or 3 times in its past. And it recovered by buildup of CO2. You actually can see this in the geologic record because you see evidence for global low latitude glaciation indicating global glaciation. And then you see cap carbonates on the top telling us that it was a buildup of CO2 that allowed us to escape. One of the things that doesn't happen frequently on the Earth, fortunately, because that would be quite catastrophic for us if it did. The reason that that doesn't happen, we think, is that the CO2 content of the atmosphere is modulated by a long-term feedback. So just to remind you, the Earth's surface is kept warm by greenhouse gases, CO2 and water vapor being the 2 most important. And CO2 is, of course, controlled by the carbon cycle, but the carbon cycle is complicated. There's an organic carbon cycle, which many people are familiar with, which is photosynthesis going in one direction and respiration and decay in the other direction. There's also an inorganic carbon cycle, which is sometimes called the carbonate-silicate cycle. And that's what we think is most important on long time scales. So here, in this cartoon, here, if we start at the left, CO2 dissolves in rainwater to give you carbonic acid. That's a weak acid. You can drink it in soda pop and it doesn't hurt you too much, but it's strong enough to dissolve silicate rocks on the continents, represented here by the mineral calcium silicate. Calcium silicate plus CO2 plus water gives you calcium ions plus bicarbonate plus dissolved silica. And then those ions collect in streams and rivers and flow down to the ocean, where organisms make shells out of calcium carbonate, combining calcium with bicarbonate to form calcium carbonate, giving back 1 CO2 to the atmosphere-ocean system, and 1 goes into the carbonates. Then when these organisms die, they fall into the deep ocean, and most of them dissolve because the deep ocean is more acidic than the surface ocean. But in some places, they accumulate on the seafloor to form carbonate sediments. The seafloor isn't just sitting there, it's spreading because of plate tectonics. And so at certain plate boundaries, the seafloor is subducted, the carbonate sediments are dragged down. Some of them are scraped off, but some of them go to great depths where it's hot and the pressure is high. And then you get these reactions reverse. So calcium carbonate recombines with silica, which by this time is the mineral quartz, to reform calcium and magnesium silicates and release CO2. And then that CO2 comes back into the atmosphere-ocean system through volcanism, arc volcanism. So if you think about this cycle is slow. It takes about 500,000 years to recycle all the CO2 in the combined atmosphere ocean system. It's not going to save us from global warming because it's way too slow. But think about what would happen if the Earth were to globally glaciate. You'd freeze the oceans over. You'd more or less shut down the hydrologic cycle. You might still have a little bit of sublimation of ice and snowfall on the continents, but you need liquid water to make weathering reactions go at any rate. So the idea then is that silicate weathering would slow down or stop entirely, but volcanism would continue. And this slide makes it look like the whole thing would shut down, but there's actually 70 million years of carbonate accumulated on the seafloor, and that would keep coming out. And there's also other types of volcanism, like hotspot volcanism that you see in Hawaii, for example. So in our models, CO2, if the Earth gets too cold, CO2 builds up, and that counteracts the cooling by the greenhouse effect. Most of the time in the Earth's history, as I already said, we don't go into global glaciation, and that's because this feedback, you don't have to freeze the oceans over before it starts to work. As soon as the Earth starts to get cooler, silicate weathering slows down, CO2 goes up, and so that's a negative feedback that helps stabilize the climate. All right, so that's actually the key to this whole concept of the habitable zone, which I've worked on and off for many years. This is a diagram of the habitable zone that was based on some calculations that we published back in 1993. The figure is from some European astronomers. You can actually tell because their numbers, instead of having decimal points, they have commas there. So this x-axis is the radius of orbit relative to Earth's. Earth is here at 1 AU. So that would be 0.1 on the inside there. The blue strip is the habitable zone. The vertical axis is the mass of the star relative to the sun. Our sun is here in yellow at 1. Down here below that are K stars, and then M stars, red dwarfs, which are of course much dimmer. So the habitable zone is much closer in. Up here we have F stars. We don't go earlier than F stars, but these are bright blue stars, and so they give off a lot of starlight, and the habitable zone moves out. Arranged here around the sun are the 8 planets of the solar system. There's 9 on this graph. You can tell it's old, but I've X'd out Pluto, which got deplanetized a while back because it's smaller than some objects that have been found in the Kuiper belt beyond that distance, right? This cryptic name up at the top, ZAMS, that stands for zero age main sequence. This is a diagram of where the habitable zone would be for the sun and for all these stars at the point where they first entered the main sequence, meaning they started to burn hydrogen. As I already mentioned, they brighten with time. All stars brighten with time. The blue stars brighten very rapidly, and the M stars brighten very slowly, but the habitable zone therefore moves out with time. So to draw this kind of a diagram, you have to pick a time in the star's history. Notice that Earth is this is at 4.6 billion years ago. Earth was right in the middle of the habitable zone. Here's Venus on the inside, and Mars was just on the outside of the habitable zone in our model. There are boundaries to the habitable zone. The habitable zone is wide. I neglected to say, because of this negative feedback in the carbonate-silicate cycle. That's a big difference between our model and Hart's models. We get the same inner edge, though, for basically the same reason. If you form the planet, move the Earth in closer than about 0.95 AU, then we get a runaway greenhouse, or a version of the variant on that called a moist greenhouse. But in both cases, the oceans end up being lost by evaporation, and then solar UV radiation photodissociates the water into hydrogen and oxygen. The hydrogen escapes, and the oxygen goes back and reacts with the planet's surface. The outer edge is it turns out there's a limit to how much warming you can get from a CO2 water vapor atmosphere. And I won't go into the details on that, but in our model, it occurs at about 1.67 astronomical units. And we call that the maximum CO2 greenhouse. That's a theoretical calculation. We do these with 1D climate models. Our group does. I'm going to admit somebody here who's, I see that popping up on my screen. There are people who don't trust 1D climate models and people who don't trust climate models entirely. So there are also empirical ways to define the habitable zone. And for instance, we can look at our neighbor Venus on the inside, closer to the sun. The Venus, of course, if you look at it in the visible, it looks like a bright, featureless planet because you're seeing the sulfuric acid clouds. But at radar wavelengths, you can look through the clouds. This was an image made by the Magellan spacecraft way back in the 1990s. And we see that there's no evidence for that Venus had water within the last billion years, which is how old we think the surface is. So that defines an empirical inner edge for the habitable zone. Venus, if it ever had any water, it had lost it by 1 billion years ago. On the outside, this is a picture that Viking took of Mars way back in the late 1970s. As you probably know, there's lots of fluvial features, evidence for liquid water flowing on Mars' surface. And most of that is on heavily cratered terrain, such as you see in this picture. So we think that most of these channels formed 3.8 billion years ago or earlier. So even though Mars looked like it was outside the habitable zone in our calculations, the evidence is otherwise. It looks like it may have been habitable in its early history. All right, so if you put this all together, then you can use that to define, the habitable zone. So I showed you that diagram, an old one of the habitable zone. This is the way we like to do them now, and I'll explain why in a moment. But instead of using distance on the x-axis, this is the amount of starlight on the planet relative to sunlight on Earth. So here at 100%, here's Earth up here again. And then on the vertical axis, instead of the star's mass, we've got stellar effective radiating temperature. The sun radiates, its surface is at about 5780 kelvins. And so the dim M stars are much cooler, about 3000 Kelvin, and an F star might be 7000 Kelvin, right? So here's, this is just, the reason we do this now is because this expands the habitable zone so that you can see it in more detail. And you can, it's now populated by all these planets, exoplanets that have been found mostly from NASA's Kepler mission, which I'll talk about momentarily. But here, this yellow curve here, that's the runaway greenhouse limit. And this blue curve is the maximum greenhouse limit. Both of those are calculated from climate models. The red curve is the recent Venus limit. That's the empirical one I just mentioned. And that orange curve is the early Mars limit, empirical limits on the habitable zone. So we like to call this region here, where we can justify it with climate models, the conservative habitable zone. So if you're designing big space telescopes and don't want to undersize your telescope, you want to be conservative in your estimates here. So, and people are actually using these to design big space telescopes. So that's the conservative habitable zone. Once you've got your telescope built and you want to use it, you can afford to be more optimistic. So then we expand that boundary and define the optimistic habitable zone. And as I already mentioned, these are Kepler objects down here, which I'll come back to. This is an older slide, and we've refined the list of interesting planets. All right, so that brings me to part 3, some recent developments in the search for habitable planets. I'm not going to go through a laundry list here, but I'll mention 3 or 4 of them. The Kepler mission is the most important thing. And this is not that recent, actually. This was a spacecraft that did its primary mission between 2009 and 2013. And Kepler monitored the brightness of 160,000 stars simultaneously for 4 years, staring at a single patch of the sky. So here's the Kepler viewing field here. It's right off the Milky Way. And why is that? So they wanted to look at a place where there were lots of stars in the sky, but that was not obscured by the clouds of gas and dust that are present in the plane of the Milky Way. So Kepler looked at this and monitored these stars' brightness to 1 part in 10 to the 5th, looking for transits of planets. The transit is when the planet passes in front of its star. And the Earth is about 1/100th of the diameter of the sun. So its surface area is, projected surface area is 10 to the minus 4 times that of the sun, because the area is pi r squared. So when the Earth passes in front of the sun, it dims the light by 1 part in 10 to the 4th. Kepler could measure the dimming to 1 part in 10 to the 5th. So Kepler's primary goal was to find Earth-like planets around other stars, right? And the reason that Kepler was flown was to define this parameter called eta sub Earth, which is the fraction of stars that have at least 1 rocky planet in their habitable zone. That's what we need to know in order to design space telescopes. Kepler got pretty good results, especially for the M stars, because it's easier to do this for M stars. And so the number that is held up since about 2015 is that eta sub Earth is about 0.2. 1 in 5 M stars has a rocky planet in its habitable zone. More recently, it was harder to do this for sun-like stars, GK stars, because you didn't have as many orbits, and they don't dim. They're bigger than M stars, so the dimming is not as big. But that number seems to be even higher. It may be that half of sun-like stars have planets in their habitable zones. We've also learned that big planets are not rocky. So with Kepler, with transit measurements, you get the diameter of the planet. There's another way of detecting exoplanets where you look, it's called the radial velocity or Doppler method. So there you look at the star and you look for the back and forth wobble of the star from the planet orbiting around it. The planet tugs on the star just like the star tugs on the planet. So if you have measurements of the planet diameter from Kepler, and then measurements, if you can follow up with radial velocity measurements, you can get the mass of the planet, and knowing the mass and the diameter, you can calculate the density. So here's a plot of various exoplanets for which they have both transit measurements and RV measurements. And this is planet density in grams per cubic centimeter. In those units, Earth is about 5 or 5.5. And what you see here, this is planet radius on the bottom. So for planets smaller than the Earth, as you go up to about 1.5 Earth radii, they get denser and denser. And then beyond that, they get less dense, indicating that they're probably not rocky, right? So we think that somewhere around 1.5, 1.6 Earth radii is the upper limit for rocky planets. In fact, a more recent paper here shows that there's a gap in the exoplanet data. This is planetary radius on the x-axis and the relative number of planets here on the vertical axis. So there's a population down here, which probably represents rocky planets like the Earth. And then there's another population up here, which is bigger planets, which are really more like Uranus or Neptune, but closer to their stars. So these are sometimes called Earths and super Earths, and these planets over here are called sub-Neptunes. I'll mention 2 more discoveries because they're things we're going to hope to follow up on in the next year. several years ago, 4 years ago, a planet was discovered around the very nearest star, Proxima Centauri. So for those who know their stars, Proxima is part of the Alpha Centauri system. Alpha Centauri is a very bright sun-like star, very, very close. You can see it in the southern hemisphere. It's actually a double star, a G star and a K star, but then there's a third star that's weakly bound to those called, it's a red dwarf called Proxima Centauri. It's a little closer to the Earth than Alpha and Beta Centauri. And there's using the Doppler method, it has been discovered that there's a planet around there in the habitable zone of Proxima Centauri that has a minimum mass of about 1.3 Earth masses. So that's very close, and I'll show you in a moment that we may be able to observe that pretty easily. Then the last development that I'll mention is there's another system that's been found from the transit method, this time from a ground-based transit survey, and this is called the TRAPPIST-1 system. The TRAPPIST-1 is an M star about 40 light years away, and it has 7 or 8 planets going around that all transit the star, so they're very well aligned in a plane, and 3 or 4 of those are within the habitable zone of their star. So they're also potential targets for observations. So here, the last thing, this is the most recent version of the habitable zone now, which has been updated with all of these developments. You know, here's the optimistic habitable zone and the conservative habitable zone. And now the planet population looks different because we've eliminated all the exoplanets bigger than 1.6 Earth radii, and we've added, here's Proxima Centauri b, that's the planet around Proxima Centauri. Here's the TRAPPIST-1 system down here at the bottom, and notice that 3 of those planets are in the conservative habitable zone, and there's 1 in the optimistic habitable zone. So those are all potential targets for follow-up observations. So that brings me to the last part, which I will also hopefully be quick on. How can we observe these planets in the future? Well, many of you have probably heard of the NASA's James Webb Space Telescope, which is a big 6.5 meter infrared space telescope that was supposed to launch about 8 or 10 years ago, and it's been delayed continuously, and it's way over budget. It's up to about $9 billion, but it's supposed to launch next October. And so that can look at some of these systems. In particular, it should do a good job on the TRAPPIST-1 system. So that's high on the priority list for JW, assuming it launches successfully in October. There's also some big telescopes being built on the ground. This is the European Space Organization's ELT, Extremely Large Aperture Telescope, that's being built down in Chile. It's got a 39-meter aperture. And just to give you perspective, the biggest telescopes in the world today are the 2 10-meter telescopes, Keck telescopes in Hawaii. So this is going to have almost 4 times the aperture. And this one, they hope to be able to look at Proxima Centauri directly by blocking out the light from the star and looking for the light from the planet. So that's very exciting, and that could happen not long after JWST flies. What we want to do in the long run, though, is that we want to do this process we call direct imaging, where you're looking for reflected starlight from the planet. You can look either in the visible or the infrared, but in the visible, it seems like that's the easiest to do it. So NASA has been studying direct imaging telescopes. There are 2 that are being considered right now as we speak by the Astronomy and Astrophysics Decadal Survey. One's called LUVOIR, the Large UV Optical Infrared Space Telescope. That's up here at the top. So it looks a little bit like JWST, but it's a lot bigger, and it operates at shorter wavelengths. There's an 8-meter version and a 15-meter version. So these are huge compared to, the biggest telescope we've flown to date is the Hubble Space Telescope, which is 2.4 meters. So these are much bigger, and this would have a good coronagraph on it. Meaning the coronagraph is something that you can use to block out the starlight and look for the light reflected by the planets around it. And there's another slightly smaller direct imaging mission being studied called HABEX, the Habitable Planets Explorer. This is only a 4-meter telescope, but it would come with a star shade. This is a star shade right there, and that's another way of blocking out the light from the star so you can see the planets around it. What could we look for? Well, we want to not just see the planets, but take spectra of their atmospheres, and we look for biosignature gases. So on Earth, oxygen is, our atmosphere is 21% oxygen. That's produced by photosynthesis. We also have about 1.6 parts per million of methane, which is almost entirely biogenic. So if you could see a planet like the Earth with both oxygen and methane in its atmosphere, it's very likely it would be inhabited. And then finally, my last slide before conclusions, this is a spectrum of the Earth in the visible. So the scale is in angstroms, which is astronomers used to like that. That's an angstrom is 1/10 of a nanometer. So the visible in these units goes from 4,000 angstroms out to 7,000 angstroms. And what you see, this spectrum, I used to work on the working group, the Terrestrial Planet Finder Science Working Group, and we wanted a single pixel spectrum of the Earth so we could look at the Earth like an exoplanet. So we used to think we'd have to send a spacecraft far away from the Earth to get this. And then some astronomers on the team were smarter than that, and they went up to Kitt Peak in Arizona, and they looked at the moon. And you see this diagram up here, this picture up at the left. If the moon is in crescent phase, of course, you see the sunlight reflected from the bright side of the moon, but on a dark night, you can see the dark side of the moon. And why is that? Well, there's sunlight that comes from the sun, hits the Earth, bounces towards the moon, and then is reflected from the dark side of the moon. So it turns out if you take a spectrum of the bright side of the moon, the dark side of the moon, and subtract the bright side, you can get a spectrum of the Earth, a single pixel spectrum of the Earth. So that's what this black curve is up here. That's data taken from Kitt Peak using these Earthshine data. This red curve down here shows the spectral features. And notice that there's 3 water vapor features here. Water vapor probably implies that there's liquid water there, so that that would be something to look at. There's a broad ozone feature right here in the mid-visible. And here, just into the near infrared, there's this O2A band here, which is very deep. And that's something that all of these space telescopes would be looking for on an exoplanet. So then to leave you with some conclusions, detectable life requires the list of 4 things that I mentioned at the beginning, including surface liquid water. Habitable zones should be defined conservatively while we're designing these space-based telescopes. There's some big ground-based telescopes that may be able to look at the closest planets, like the one like Proxima B. The James Webb Space Telescope may be able to look at the TRAPPIST-1 system. And in the long run, I'm hoping that the astronomers pick either HABEX or LUVOIR, and we may get spectra of planets around sun-like stars within our lifetimes. Okay, so that's it, and I'm happy to take questions.
Thank you, Jim. That was fascinating. Any questions out there? I don't see any hands raised or anybody speaking. There we go, Hiroshi.
Yeah, Jim, thanks for coming. Well, staying at your office or home. Nice lecture. I have questions about the habitabilities on Mars. You said Mars was in habitable zone 3.8 billion years ago, but you think now it's outside of a habitable zone?
Actually, it's just the opposite. We think Mars was outside of the habitable zone the way we calculate it with climate models 3.8 billion years ago. But now that the sun has brightened, Mars is now
Yeah.
inside the habitable zone. And I should have pointed that out, that it's, you know, so that implies that if Mars today had an Earth-like atmosphere, it, you know, if you had the Earth out at Mars distance, it should be habitable. It would build up CO2. And of course, that doesn't happen with Mars because it's too small, it doesn't have volcanism, and it's lost most of its atmosphere.
Yeah. So you think there's waters on Mars surface now?
Not at the surface, but there, you know, all the models suggest that there's subsurface water on Mars. I think you have to go down at least a half a kilometer to a kilometer to find it. And so, you know, there's certainly astrobiologists that want to do that, but that's difficult. We've only been able to drill down a few feet into the Martian soil, and I think you have to go a kilometer. So we
You
need
think all evaporated out, surface water got evaporated out?
Yeah, so it forms ice there. The mean global temperature on Mars is 212 kelvins, minus 60 centigrade. So Mars, you've got big, you know, ice caps, which are a combination of CO2 and water ice. But if there's any liquid water, it's only there transiently at the surface.
Yeah, I have another question, Jim.
Go right
you
ahead,
said-
Hiroshi.
You suggested that use of oxygen and methane spikes spectra to look for life. But according to your model for Earth evolution, that will apply only to very advanced planet. Your model is that until 2.5 billion years ago, there was no oxygen in the atmosphere, only anaerobic bacteria. So that's, according to your model, is the first half of the Earth. So unless other planet had gone through evolution like Earth, you wouldn't see any oxygen in the atmosphere. Only things you may see is methane.
Yep, I totally agree with that, Hiroshi. And, you know, for those who haven't followed this, Hiroshi and I have discussed, debated, you know, when oxygen rose on Earth. You know, what you just said right now, Hiroshi, is correct. You know, I think that oxygen first rose about 2.5 billion years ago. And so before that time, which is almost half of the Earth's history, you wouldn't see oxygen. We do think you'd see methane. And so you know, that's a testable hypothesis. So with LUVOIR A, the big version of LUVOIR, they're actually hoping to find 30 Earth-like planets within the habitable zone. And so if they were all analogous to the Earth, you know, if they were all around G stars and, you know, had been there for 4.5 billion years, you know, and if they all had life, we'd expect to see oxygen on half of them and methane on the other half, right? And of course, if they don't have life, we might see neither of those gases. So,
Jim, I have a question regarding the carbonate-silicate cycle there. You mentioned in the subduction zone that the product was calcium carbonate and quartz, silica as quartz. Does the quartz form directly, or is that a hydrothermal transformation from some other polymorph?
you know, the silica forms opal on the seafloor. So that's the mineral that is formed, and then that opal gets buried and gets transformed into quartz. And actually, if you ask any more detail on that, I'll throw it off to Hiroshi, because Hiroshi is a much better mineralogist than I am.
Yeah, so as a ceramist, we were always taught it's very difficult to form quartz, that it usually transforms from some other polymorph. I'd like to hear more.
Hiroshi, I'll let you respond.
Well, you don't have to have pure silica. SiO2 could go into any number of silicates. So that's just a simplified chemical reaction you write to.
Yeah, I'm an atmospheric scientist, so I really oversimplify the geochemistry sometimes.
Oh, thank you. Other questions? Well, I will say that this Zoom has been recorded. We're going to be including this Zoom as one of several dozen lectures on our college's 125th anniversary website. We're actually starting with this one and getting ready to record the rest. So over the course of the next several months, if you look at the College of Earth and Mineral Sciences website and look for the anniversary portion, you'll see a whole host of presentations, some of which have already been presented at the Village, but weren't recorded at that time. So we're re-recording them. And all the future conversations with colleagues, presentations will be recorded and put up there. So there's a wealth of stuff to look at there and on its way. So Jim, thank you very much. That was fascinating.
Thanks,
And
Jim.
Okay, well, thanks for the invite. Thanks for showing up, Hiroshi, and also everybody else. So I hope you have a good lecture series out of